Is that good? Can you all hear me now? Okay. So this is going to be, at first I want to thank the Simons Institute and the folks running the Big Data program and for organizing this workshop. It's an honor to be here to listen to all these wonderful talks. What I'd like to do today is something a little different from the talks that you have seen and will be seeing in the course of this workshop. A lot of what we've been seeing here is all about succinct representations of data, primarily. Okay, so a lot of things that we've been seeing in this workshop about succinct representations of data, primarily from a computational point of view. You have lots of data, you have to compress it, and you want to maintain these small fingerprint sketches, what have you, to represent the data, and you can do things homomorphically or otherwise on it. But what I'd like to talk about today is the issue of maintaining, if you wish, succinctness and locality for a completely different reason altogether, from the point of view of data analysis. So this talk is going to be, it's about joint work with this is joint with my student Parashwan Raman, who is somewhere in the audience here. It's partly an attempt to sort of lay out some new, what I think are new questions in how we do data analysis. And so there will be, hopefully there'll be some interesting questions at the end for people to discuss. So it starts off with your classic mining pipeline, right? So you have lots of data, you clean it, something like 90% of what your work is basically data cleaning. You clean, and then you do some exploration with the data. You maybe bring in other kinds of data, you build some models, you do something at the end, you declare that no, you can't go on this plane today because you're on the no-fly list, or something like that. And when we look at how to design algorithms for doing learning of various kinds, and in the Big Data Bootcamp we've seen, there are many different ways of thinking about this. From a computer science point of view, you say, okay, give me a cost function. I will optimize the heck out of it. I'll just get you the best approximation, or I'll try to get it optimally, or do what I can with it. If you're doing, from a statistical perspective, you're trying to get a good estimator, you're trying to do minimax bounds in the estimator, you're trying to get something reasonably high quality for this problem that you want to solve. And there are many ways you can go about doing this. We've seen a lot of work on how to do this. But all of these methods, or most of them, for the most part, look at some kind of global optimum. They want to look at some global optimization, and they want to solve that well. And that's all very well, except that if you are the person who's being mined in some sense, if your data is the data being mined, then it is not of any great consolation to you that the algorithm works awesomely if you're the one being pushed off a plane, for example. Or if you're the one whose medical records are not being relayed properly, you're the one whose diagnosis is not quite correct. In other words, while the goal of trying to give results for learning algorithms that have global quality is a valid goal and an interesting goal, there is also this question of locality. And this question of locality has become even more important as the results of search have become more personalized. I think everyone knows that all of your searches and all of the things you do are very personalized now. You get results targeted to you. If you have your Google web history turned on, it gives you results targeted to you. If you go to Amazon, it gives you recommendations for you. And if you talk to people who do these kinds of works at the big companies, they spend most of the time doing personalized search, doing personalized mining. They don't look for the global solution, they look for local things. And so one thing that would be nice to have is a way to say, well, I have made this inference on this collection of data. I have made, in particular, an inference for any possible point. Let's say I have a classification algorithm. I've labeled a point as being on one side or the other of the divide. How sure am I of that decision? How confident am I that this is actually a good answer for that point, and not overall? Overall, it might be great. And so there have been sort of examples of doing this kind of thing in the past. One very good example of this, I think, goes back to classification. So, of course, you all know if you have a classifier, the goal of classification, you want to have some kind of decision boundary that separates points labeled plus from points labeled minus. In the easiest case, you have some kind of linear classifier, and you have some description of the boundary, in this case, a hyperplane, some kind of w dot x plus p. It tells you how to decide plus or minus. But once you do that and a new point arrives, how do you know how reliable your answer is? Of course, there are many, you could say, I'll look at the margin of the classifier, I'll see how far I am from the margin, and that gives me some clues. So I measure the distance to my hyperplane, and I am 5 units away from it. So, okay, what does that mean? What does it mean to be 5 or 10 or 15 units away? So there's been some work on this. A number of researchers looked at how to derive some meaningful information from this classification boundary with the proviso that you didn't want to actually necessarily put the problem of modeling this into this. You could actually come up with a probabilistic model. You could build a model and do the classification with that. But suppose I just gave you a classifier. Right? Suppose I'm part of some large problem and I say, here's my classifier. And you want to, in some sense, post facto figure out what might be reasonable for this. So there's this technique called Platt scaling that comes from John Platt, I think, from 1999. And what he said was that, okay, you give me a classifier. What I will do was, he sort of looked at a number of different data sets, and he said, okay, what it looks like is that you're having some kind of sigmoidal behavior around the decision boundary, especially if it's a good decision boundary. So let me try to fit a sigmoid to this data. So in particular, given my classifier, given a data point, what I want to estimate is the probability that my label is equal to 1 given the point. And so I'm going to say, okay, I will model this by some kind of sigmoid, and I will try to fit these parameters, capital A and capital B, given some training data. And what you end up with is this conditional probability. And of course, then the parameters are estimated, by the way, using maximum likelihood or whatever. So what this does is it converts a classifier, a global result that has optimized some function using hinge loss or whatever have you, into a number for any point that says how likely is this point to be correctly classified, or how strong is my belief in the answer I'm giving for this point. Okay? So what I want to talk about today is an attempt to do something similar in a setting where it gets a little bit harder to do this, in an unsupervised setting, where you don't really have that much label information. And in particular, I'd like to do this for clustering. So of course, everyone knows what clustering is. The goal is to group things into different clusters, and there are a gazillion different kinds of clustering algorithms. Every year, I think there are at least conservatively 10,000 new papers on clustering, maybe 20,000. I don't know. I probably have to review half of them. So there, there's k-means, there's k-medoids, there's hierarchical spectral. You give your favorite thing, and you can take all kinds of permutations and combinations of these, put them in string. You have a string of clustering words. But when you get your answer, how do you know that this answer is actually any good? Because clustering is one of those annoying problems where, for the most part, it's unsupervised. It's usually an exploratory technique. You say, okay, I will take my data, I will cluster it, and I will get some answer. And I'm not always sure what the answer is because I don't always have a nice model. I'm not doing, say, for example, learning a mixture of Gaussians. I'm not doing LD. I'm not doing something with a well-defined probabilistic model behind what I'm doing. I'm just clustering some data. And so I do need to know how good my answer is. And as a consequence, there's been a number of efforts to try and understand the quality of clustering algorithms. There's been a whole lot of work on this. So for example, there's a bunch of work on this, but they can roughly fit into 3 or 4 different categories. One is this thing called internal validation. If I have a clustering, a good clustering is one where clusters are tight and they're far. Right? So you can actually quantify this. You can say, okay, tightness is the width of a cluster, far is the intercluster distance, take some ratio, you can do things like this. You can say, okay, this is a measure of how good the clustering is. You can also do things like external validation. If you actually have a reference, some kind of reference clustering, some kind of ground truth, some amount of data that you actually have checked, then you can do something called external validation. You compare to the ground truth. This actually brings up a whole separate story of the geometry of the space of clusterings, how you compare clusterings, what are appropriate distance functions, and so on and so forth. And there's a lot of work on that as well. And there's also this thing which is often called relative validation, which says, okay, I have something like k-means. I want to figure out if my answer is good. And so what I'm going to do is I'm going to run it a bunch of times, look at the different answers, and see how different they are from each other. And if I keep getting the same answer over again, I feel more confident that this is a good answer. And this brings up another topic, which is related to all this whole issue of stability in clustering. How do you figure out if a clustering answer is stable? There's been some work from people here on various notions of stability. For example, you might say a clustering is stable when I perturb points a little bit, I don't change the answer too much. Or a clustering is stable is when if I know there's a good answer, I can find it efficiently. If there's an answer that's known to be close to the good answer in a kind of a Hamming sense. There's been a bunch of works on that. But all of these methods, again, are global methods. They give you kind of a global view of how the clustering is working. And again, in this sort of more personalized view of how we look at data, we want some kind of short certificate for a point that says, this was my label for this clustering, and I'm pretty sure that this is a good labeling. Or I have some confidence based on what I'm doing that this is a good label to have. So this is the problem. I give you an arbitrary clustering of data. Preferably, I know nothing about where it came from in the most general case. I may know something about the distance spaces defined on. And I want to be able to assign some kind of confidence bound to points in the clustering, or even new points that come up. I want to say, okay, this point is assigned to this cluster, but I only have this much confidence in doing so. And I want something that has a kind of a notion of scale when in these numbers that's data independent. Maybe it's a probability or something like that. It should be agnostic as far as possible to how I generate the clustering. Again, this whole idea of having a data pipeline. In a pipeline, you don't always have control over where your data comes from. So if it's presented to you, you'd like to be able to work with what you have. Okay? It should work given a single clustering. I'm not talking about a model or an ensemble. I'm just have a single clustering. But I should be able to have, it should be general enough that I can use it to compare different clusterings if I need to. It shouldn't be very specific to one thing. So this is kind of the goals to set it. And of course, since I wrote these 4 points and I want to hit them all one by one. But these are also reasonable things that you'd like to have. Okay. And one minor point, this question, since it always comes up, and maybe some of you are thinking about this, I'll bring it up right now. And there's a whole area of what is called outlier detection. And it sounds very similar to this. It's like, oh, there are these points, they're not good points. I want to find out which points are not good and eliminate them. And outlier detection in the theory world, at least, is a standard way to think about some of these questions. You can say, I have a collection of points, I want to find an optimal clustering, and I'm allowed to throw away an epsilon fraction of points. In machine learning, you have this idea, you can have a misclassification error, you can have some small set of points that are misclassified, that's okay. But you don't want to have too many points misclassified. This is one way of capturing outliers. So there are more regularized ways of doing this as well. You don't have to have this hard thing, I take it or don't take it. But outlier detection is subtly different from this kind of problem in the sense that in an outlier detection problem, you don't want outliers because they really mess up your cost function usually, especially in L2 sense. They go out and they pull things out like crazy. So you have to do all kinds of work to make sure they're not in part of your cost function. But they don't necessarily change the assignment itself. Usually they're outliers to a single cluster. You're probably going to put them in the same cluster anyway, but they're just messing up your cost function. They affect your algorithm. Whereas with things like the problem of validation, the problem of finding a certificate for a label, it is quite possible that the cost does not change very much, but the label does. And because a label is kind of a binary thing, that can change the decisions downstream quite a bit. So you do want to know to what degree this label is. So they're slightly different in some way. I will also talk about probabilistic modeling a little later on, because that's another area where you think, okay, if I have a probabilistic model, I'm getting these belief values automatically from the mixture of Gaussians or what have you. That's a more specialized setting. Okay. Any questions so far? It's all very high level, I know, so I'll get into some technical details in a bit. So again, just to remind you all, the goal is to, given a clustering of points, find some kind of confidence numbers, a number that's attached to every, or a set of numbers or a vector that's attached to any single point that gives you some sense of how reliable this clustering is with respect to the data, or how trustworthy your labels are at that point. Okay. And the idea that we're going to use is this general notion of an idea of region of influence. And so the core idea, which we'll try to formalize in a bit, is that in some sense, things have regions of influence. Clusters have regions of influence. They own a certain portion of the space. And that's why you've partitioned things. And so a point should be in a cluster if the point treated as a cluster by itself had a region of influence that kind of overlapped the cluster you want to put it in. So what does that mean? It seems a bit vague. So in particular, let's take an example, actually. Don't even read this. So suppose I have points in a line. I have the easy case, right? I'm clustering points in a line, and I have these clusters. And the color resolution is not as nice as I should have made it, but there are 4 clusters here for the 4 points. There's a blue, a red, a light blue, and a dark blue cluster there. And so now you get a point coming in, and you would like to know, where should this point be, and what kind of confidence do I have that this points label is indeed what it is. So I probably want to put this in what I'll call the red cluster for now. And what I want to say is that if I look at now what this point would be like if it were a separate cluster all by itself, it would be, in some sense, stealing some mass from the red cluster, quite a bit of it, in fact, and stealing a little bit of mass from the blue cluster. So it is stealing volume from the red cluster, a lot of it, and so it is much more likely to be associated with the red cluster. That's the rough idea here. And so of course, what we're doing here when I say area or volume, I'm actually talking about distances. I'm saying that the distance to the red center, the center of the red cluster, is much less than the distance to any other center. And so that is going to increase its likelihood of being in the red center. And then if you look at, for example, a lot of these mixture model learning, so if it's mixtures of Gaussians or in general Bregman divergences, what you see is that the resulting algorithm, the assignment probability of a point to a cluster looks exactly like this. It says the probability of assigning a point to a particular Gaussian is roughly e to the minus L2 distance squared between the point and the center of the centroid. If it's some other general Bregman divergence, it's e to the minus the Bregman divergence between the point and the center of that cluster. So this idea of using distances is actually, it shows up in many clustering algorithms already. Okay? But distances are not quite enough. I mean, distances capture a little bit of what you would like to see in this problem, but they don't quite capture everything. They capture, in some sense, a one-dimensional rendition of what you want, because they're just lines. In general, you could have a clustering, a bunch of points. Don't worry about those lines for now. I'll explain what that means in a bit. And if I have a new point Q, I could measure its distances to 3 different cluster centers, the C, C prime, and the C star. And I could make some sense, oh, you know, it's so far from this, it's so from that. This is maybe the ratio in which it should be assigned to the 3 clusters. But of course, that's very unlikely to happen. Most of the time, if you run a clustering with, say, different random scenes, you're going to try and assign Q to the C star, because of this kind of shielding effect that it has. And what they're saying is that there's some kind of spatial structure that you'd like to exploit to try to understand where a point should go and what its true label should be. So if we develop that further, we get to what we want to do. So again, there's this property of clustering called the Voronoi property. Again, I don't know, probably most of you already in the audience know about Voronoi diagrams and the Voronoi property, but just in case there's a few of you who don't, a Voronoi diagram is a partition of space. If I have a bunch of points, it's a partition of space, so that in each cell of the partition, one of those points is the nearest neighbor. It's also called the post office problem. So in this particular partition, if you look at that point at the bottom there, that cell around it, any point in that cell will declare this to be its nearest neighbor. Now clusterings, many clustering algorithms yield a clustering that has what is called the Voronoi property. Namely that for any particular point, the cluster you want to assign it to is in fact its nearest neighbor. So the clusterings induce a partition of the space. And this property gets used a lot when doing clustering. It leads to efficient algorithms and so on and so forth. Okay? So can we use this property of clustering, this sort of natural property of clusterings, to actually define this notion of volume capture? And so the idea here is that, suppose I have 3 points. Okay? So I have these 3 points, and there are 3 clusters there, and I form this Voronoi diagram. So it would look something like this. Okay? And now a new point comes in. The new point comes in here. I will now pretend this new point was a cluster by itself, construct the resulting new Voronoi diagram, and it looks like this. And now look at this Voronoi cell of this point very carefully. What it essentially has done, it has stolen volume from the 3 Voronoi cells that you already have. Okay? So in particular, if you look at this volume here, you can say that this volume is divided into these 3 parts for these 3 clusters that it's involved with. And so you can define this ratio of the ratio of, say, this volume, R3, to the overall volume of the cell. And this is, in some sense, the amount of volume that that point has stolen from the cluster C3, and so on and so forth. In general, for each point, you get this vector. We'll call this the affinity vector, and it's a fractional area stolen from it. And this, of course, is a point in the simplex, the value sum to 1. Okay? So this will define as the vector of affinities that we will now sort of use as our coding, if you wish, to understand the affinity of points for clusters. So the couple of interesting properties. This idea was first used back in the 80s. So in the area of GIS, this was used to do interpolation. And so there the problem was I give you a bunch of points, and they have scalar values. I would like to interpolate a function between them. And I don't want to put any modeling assumptions in the data. I don't really know what the function is that would appropriately fit. So this idea of natural neighbor interpolation says, for each point in the domain, in the convex hull of these points, you will get a vector of affinities just the way I described, by computing the Voronoi diagram, inserting the point in, looking how much area it steals. Those weights, the convex vector there, this vector sums to 1, is used to compute a convex combination of the weights of all the points that are involved in this. And that gives you an interpolant. And this interpolant has various nice properties. It's continuous, it's differentiable except at the data points, and this and its variants have been used a lot in the GIS community. So that's where this first comes from, back in the 80s. And so what we're going to use here is mainly just the vectors themselves. We're not going to actually do any interpolation. We're just using the vectors of these ratios. And you can make a couple of observations. If a point, you can never have 2 values that are more than 0.5. So if you have 1 value that's more than 0.5, that's in some sense the strongest assignment. And so the maximum affinity value that you have is also a scalar function, is also a useful proxy for this entire vector. You could also take the entropy of the entire vector. Since it is you can act like a distribution, it gives you some measure of the skew. Like the more spread out the points assignments are, the higher the entropy will be, and therefore the lower your confidence will be in its assignment. So there are various things you can do with this. And so that's the basic idea. The basic idea is use this geometric structure of the space and of the clusterings to define this notion of an affinity for points. Okay? And it has the advantage of being, relatively easy to visualize. If you take a bunch of points up there, you can draw nice contour maps. You can do things like these 2 dimensions. You can draw these contour maps to show you where regions of high instability or low affinity are. And you can again see, okay, there's some region here which is very unstable because you're not quite sure where this point should go, and so on and so forth. This is not necessarily the best visualization in the world, but it shows you that you could visualize these things with scalar functions. Okay, but this is not really enough in some sense, because you often have a notion of importance for a clustering. You have weights, you have density functions, right? You say, okay, this cluster is somewhat bigger than that, it's got more points in it. You'd like to be able to capture that as well. And so it turns out the important property that you want to keep is that this Warner diagram has polyhedral cells, because we'll need that later for computations. And so you want to make sure that everything stays polyhedral. And so there's a very nice structure from computational geometry that generalizes the idea of Warner diagram. It's called a power diagram. Just like in a regular Warner diagram, you have this distance function, and this is used to construct the boundaries. Basically, the boundary of any Voronoi cell is the place where these two things become equal. So dpx is equal to dpy, where this is the distance function. You can do the same thing in this sense, where you now essentially shift things up and down by a weight function. And intuitively, what this is saying is that if the weight of a point is large, then the effective distance to it is less. So you can reach out and grab things that are much further away. And so that's what you get there. You get these larger circles. The circle, the radius denotes the weight. And so now this point is pushing out and grabbing things where that line should have really been here. It's actually back there. The good thing about the power diagram is that it guarantees polyhedral cells. You get another diagram that has the lines or hyperplanes. You don't get curved objects. If you remove, for example, the square root, a square, just the Euclidean distance minus the weight, you get these curved parabolic arcs, and that's not nice to deal with. So it's just like technically deal. So once you do that again, you can do things like this. You can say, for example, again, we had our familiar contour diagram with all these points. You had these regions of high instability in the middle here. And now if I suddenly increase the density, there's no longer much ambiguity about where you should cluster points. That whole region of uncertainty just goes away. You only retain some other portions of it. So using the density function, you can actually capture a little bit more about how your uncertainty about how these things are. This generalizes to other spaces. If you're clustering with Bregman divergences, they all have a very similar structure. It's known that for Bregman divergences, the appropriate Voronoi diagrams also are linear if you define them in the correct direction. And so you can do the same trick there. This, in some sense, it works in the sense you can define this with kernels, but I'm not going to talk about kernels, but there's other technical difficulties with computing these things with kernels. But you can get the same structure there. So this notion is somewhat general. You can capture many different kinds of classes of distance functions, which is good because your clusterings can come from different sources. Okay? So how do you compute these affinity vectors? So it turns out in low dimensions, this is relatively easy. In 2 dimensions, for example, you can compute a Voronoi diagram in k log k time. You can intersect 2 convex polygons, which is what you need to do to get these shared regions. To compute the volume of a polygon, you want to triangulate it, because once you triangulate it, each triangle takes constant time to compute the area for, and you can triangulate a polygon of size k in linear time, so things are pretty easy. So if you have a query point in roughly k log k time, where k is the number of clusters, you can compute an answer. In 3D, it gets a little bit harder. The Voronoi diagram itself is bigger. It's of size k squared. And so that's the dominant term in all the calculations. The rest of them are still relatively easy to do, but because of that k squared term, you pay that much time per query. Of course, all this breaks in high dimensions. Once you go to d dimensions, the Voronoi diagram of d dimensions is roughly k to the d over 2, k to the ceiling of d over 2. So none of these things really work. You can't actually expect to compute any of these things in higher dimensions. So what do you do? Of course, the answer is to approximate. You want to get some kind of approximate estimate of what these affinities are. Right? Again, the goal is to get the small certificate for each point that gives you some sense of where its true cluster centers are. How are we doing on time? Okay. So what do I want to do? What I want to do is, given some epsilon parameter, some epsilon greater than 0, I would like to find some approximate affinity vector that has a small L infinity distance from the true affinity vector. Okay? And there's a very easy way to think about this problem, that basically what I'd like to do is sample. Suppose I can sample a point from the Voronoi cell of P. I find its second closest neighbor. Of course, its closest neighbor is P. So find its second closest neighbor, increment the count of the neighbor, and do this over and over again. At the end, I get a bunch of counts, and I normalize them. And of course, it's easy to process each sample to make this decision. You just have two questions to answer. How many samples do you need? And how do you sample from the Voronoi-Selov point? So the first part is, again, relatively easy. There are standard sampling tricks you can do to this. I mean, basically, something like 1 over epsilon squared samples will suffice. If you can sample uniformly from the Voronoi-Selov, you can get an answer for this, and it'll be within this error bound. The standard, epsilon sampling, VC dimension type arguments, or even other way. But the second part is it's a little bit, takes a little bit more thought. How do you sample from the Voronoi-Selov point? Again, you remember, you're in a point high dimensions. One thing we do know is that the Voronoi-Selov is a convex body. Okay? It's convex, and it has an easy membership oracle, because all I have to do is check these k points to sort of see, is it closer to that point than to any of them? So that part is easy. And luckily, there's been a long line of work, and there are people in this room like Santosh and others who've done a lot of work on this. If I give you a convex body in high dimensions and I want to sample from it uniformly, all I'm given is a membership oracle, how do I do this? And so there's a whole long series of results starting from the classic by Dyer, Friis, and Kannan, which Ravi Kannan is right here, and which I think roughly was the original algorithm ran something like d to the 26th time. And right now, I think this is, if I'm not mistaken, the best bound possible. Under some conditions, you need d to the 4th samples to get d to the 4th, oracle calls to get a uniform sample from the distribution. And in fact, this works for other distributions as well, not just uniform distributions, many other kinds of distributions. This algorithm is somewhat complicated. In practice, you can do something a little simpler. And this is a nice method called hit and run sampling. It's a very nice trick that I thought I'll just sort of mention here for people who may not know about this. And the way it works is basically you have your convex set, you take a point, you choose a random direction, and you extend out to the boundary. You can do this via bisection search using the membership oracle, and then choose a random point along that boundary, and then repeat again. And so this process actually can, with appropriate conditions on where you are in the beginning, can be shown to converge very quickly. And in practice, it actually works quite well to actually get this answer. Okay. One final trick. So far, all I've described is a sampling procedure that will be polynomial in the dimension, which is okay, but it's still not great. But it turns out you don't even need that. So let's limit ourselves to the Euclidean distance for now. So the K clusters induce a sort of a K-1 dimensional subspace. And there's this general kind of folklore thought in clustering that if you have data that's K clusterable, all the action is happening in K dimensions. There's really nothing interesting happening outside it. Right? And there's some formal results along these lines. This is a general kind of feeling. And so here again, you can formalize this. You can say, look, if I'm measuring, say, Euclidean distance squared, you can decompose it into the component along the subspace and the component orthogonal to the subspace. And now if you look at the Voronoi diagram that you get, it basically consists of a Voronoi diagram in the K-dimensional subspace with extrusions outwards, uniform extrusions outwards. So from a volume sampling point of view, you don't actually care about it. You can actually slice the space down and just sample in that space. So this actually means that your effective dimensionality is only K, it's not D. And so this improves the bound you get in that. So to summarize, if you're given a clustering and you have a query P, you can, and I should point out that none of this depends on the number of points that you had clustered in the first place. It only depends on K and epsilon and not even the dimension of the space, at least for Euclidean distances. So you project the clusters to a K-dimensional space, you sample uniformly, compute these frequencies, and you just return the approximate Finney scores. And again, the running time is poly in K and 1 over epsilon, and they're, in practice, actually it runs very quickly. You get order of milliseconds per query. So what I'd like to do, since I'm claiming a couple of things here. I'm claiming that, first of all, this problem is interesting, and that secondly, that this approach is a way to get at the idea of local certificates for points. That you, in some way, by doing this weird thing here, you can actually get at a sense of how reliable a clustering label is for a point. So in order to convince you of this, probably the only way to convince you is to sort of maybe show you a number of different experiments you can run. Sort of say, okay, look, this seems like a right thing. This seems like it's doing the right thing. It's by no means conclusive. This is sort of early stages of what we're thinking about here. But there is some initial encouraging evidence that suggests that this might be a reasonable thing to do. So for those of you who work in machine learning, you probably know what this is. This is the MNIST database. It's a database of digits, basically all clustered and labeled. It's nice to play with, and it's been played with to death. And what you can, basically you get the data, it's labeled in one of 10 different clusters of different digits and their images, and the goal is to cluster them or do something with them or build classifiers or what you want. And so here's a little experiment where we took an arbitrary clustering, just run k-means or something else on this, and then computed the affinity scores and the max affinity, which is we'll call the stability, for different clusters, okay, for different points, and then took points that had high stability and points that had low stability, and actually took a random sample from the top 10%, lowest 10%, so we didn't really bias around. And so this is what you get. If you get, the fuzziness here, by the way, is just in the resolution on the screen. These are the images the way they are. If you look at points that are highly stable, what you actually get is what you expect. You get points that are fairly clear. This is a 0, a 6, a 4, and 9, and they're really reasonably clear as far as possible with this data. And if you look at points that are highly unstable, again, without knowing how the clustering happened and just by running the stability, you get points that are a lot more ambiguous. Now, is this a 0? Is this kind of a 6? Or is it a 0 with a little line attached to it? This 4 and this 9 look almost similar, and so on and so forth. So in some sense, you can see that, that there is at least a correlation between the numbers you're computing via this affinity calculation, which is completely oblivious to the data, just looking at the geometry of the data, and the actual answers you're seeing from this. Another interesting application where looking at affinity scores becomes interesting is in what I'll be calling active clustering, what I can call active clustering, what people have looked at. And the idea is that in many problems, what you'd like to do is, since you have a lot of data, you would like to subsample the data to solve your problem, but it's not always obvious how to subsample the data to get things that are relevant, especially for things like clustering. And so somehow, if I knew that there were points that I wanted to pick that were informing the true decision boundary, much like how active learning works, I would want to pick those points first. And that's, in some sense, what these affinity scores allow you to do. They allow you to, they allow you to quickly, so for example, you can run a very quick k-means plus type clustering initialization, get some very crude clustering, compute the affinity scores with respect to crude clustering, and then sample points based on the affinity scores. In other words, take some points that have low affinity, which give you the skeleton of the data, and take some points that have high affinity to give you the core. And it turns out that with sampling very, very few points, and again, this is all empirical, I don't have formal bounds for this, you can actually get clusterings that are equivalent in quality, and you can get them much faster. So in some sense, what you're getting with this affinity calculation is a kind of a skeleton of the data, the relevant skeleton for decision boundaries. Not a core set per se, but a skeleton of some kind. And in fact, we have ongoing work with Kilian Weinberger from WashU on speeding up other kinds of classification algorithms, the transductive SVM and other methods using the same idea. And we have some very promising results there as well. Another place where these scores are useful is in doing model selection. Again, one of the biggest thorny issues in clustering is this whole problem of model selection. And again, if you have if you either have a probabilistic model, or if you have some criteria like the AIC or the BIC or other insert letter name IC criterion, you can try to determine what the right number of clusters is for your problem. But in general, there's no easy way to do this. And basically, you stare at charts like this and you look at, oh, there's a big bump somewhere, and maybe that's the right. And there's very crude techniques like this. And this basically is because the cost of your clustering always gets better. If at the end you put all your points in a single cluster by themselves, everything looks great, and that's why you need to regularize in some form. And so there are many regularization ways of dealing with this. So one thing that's interesting with looking at the affinity scores is that the affinity scores don't necessarily keep increasing or decreasing monotonically as you partition your clustering. If you look at if a cluster which is very good and you split it, the stability of these points just goes down a lot, because now I'm confused as to where to put them. I could go one way or the other. And so if you actually look at plotting the average stability of a point set as you change the number of clusters, you start seeing these peaks which, hopefully not coincidentally, exactly match the true number of clusters in these data sets, which are kind of data sets that we know of in our ground truth data sets. So again, there's some hint maybe that you can use local structuring of stability in an aggregate sense to get a global sense of what the clustering looks like, even though there are other methods as well to do that. But this gives you both the local and the global at the same time. So there's a number of questions about this. I mean, a lot of this work is very sort of exploratory. We're trying to understand exactly what's going on here and whether there's any formal way of explaining all these things. And so, in particular, can you correlate these affinity scores with the probabilities you extract from say, a model? And so one experiment that we had done was to say, okay, let's, for example, run an EM-type algorithm and try to learn a mixture of Gaussians and look at the soft assignments you get for clusters and compare that to the affinity scores you get here. And in many different examples, what we found was that there was a very, very high correlation between the vectors you got from a probabilistic algorithm and the vectors you got from the score here. So again, there's some evidence that these things are capturing the right kind of notion, but again, we need more understanding of what's going on here. Another thing that we've been looking at is, the affinities or even the maximum affinities define a vector or a scalar field of the data. There's been a lot of work in the computational topology community on trying to understand how to cluster data from a topological perspective. What, of course, they're missing is, or they, by design in some sense, is the geometric structure underlying the data. They've been looking at topological constructs. And so one thing that I've been, that we're interested in is sort of, can you look at things like persistence, which are this topological notion, which is essentially like a noise removal notion, but it's a very powerful idea in topology, to build over the scalar field that you get from these affinities, to combine essentially geometry and topology to understand the structure of the data. Again, the goal being to give these local certificates for quality of an assignment. So a more basic algorithmic question, can you compute, since we care about the skeleton, these points of low affinity, can you compute them quickly without having to lose over the entire set of data we care about? Again, there are some heuristics, there's a progressive quad tree-based process you can use to sort of progressively refine your scalar field, but it would be nice to have some more formal arguments for, I can get the points of stability, which are at most something, and so on and so forth. And other applications, we've seen a number of applications. There's some that I haven't mentioned that we have in our work, where you can use these things to kind of accelerate the process of clustering, and you can use it essentially as a core set of a kind, where the points of low affinity are your skeleton of the decision boundaries that you can use to solve problems, other problems where this can be looked at. And on that note, I will stop and not keep you from your coffee anymore. Thank you for listening. Yes. Right. So there are a couple of problems with this approach. First of all, the notion of stability for a clustering itself, although people have looked at it, the conclusion has been is that it's not quite clear how to define it. Some of these notions of stability that I mentioned, they're problematic in certain ways. So if you're talking about this, for example, how to cluster to maximize the sum of affinities, for example, would be one thing. I have thought about this. We don't know how to do it yet, but that's something that we thought about. Okay, if I said that my goal is to maximize the sum of affinities, how would I go about doing it? So it's a good question. I don't know the answer, though. Yeah. Okay. Thank you.